Welcome, and thank you so much for joining me today for this explainer. I am truly glad you're here. Today, we have a really beautiful topic to unpack. We are going to gently peel back the layers of the world around us and look at the chemical classification of matter. Let's take our time and explore this fascinating subject together at a completely comfortable pace. So please, get your notebooks ready, make yourself comfortable, and let's begin. We'll start with a very simple question about a familiar, everyday object. Think about a fresh glass of milk. Is the milk you drink truly pure? Well, it seems like a straightforward question, right? But as we're going to see, a scientist looks at the world quite differently than we typically do in our everyday lives. Here is our roadmap for today's explainer. Think of it as a gentle syllabus so you can easily organize your notes. First, what does pure really mean? Second, pure substances and mixtures. Third, solutions, suspensions, and colloids. Fourth, understanding the Tyndall effect. And finally, physical versus chemical changes. Okay, let's dive right into our first section. What does pure really mean? It's genuinely fascinating to contrast two perfectly valid but very different ways of seeing the world. When you or I go to the grocery store, we consider milk pure if there's absolutely no adulteration, meaning nothing extra like water or artificial chemicals has been added to it. But to a chemist, well, the word pure has a very strict meaning. A pure substance must consist of a single type of particle with a completely uniform chemical nature. Because milk is actually this complex, beautiful blend of water, fats, and proteins all mixed together, a scientist would confidently tell you that milk is absolutely not pure. It is, in fact, a mixture.
So now that we know what purity means in chemistry, let's move right along to Section 2, Pure Substances and Mixtures. Let's look really closely at pure substances. They basically come in two varieties, elements and compounds. Elements are the absolute simplest form of matter. They literally cannot be broken down any further by chemical reactions. Think of shiny gold, sturdy iron, or the oxygen we breathe. Compounds, on the other hand, happen when two or more elements chemically combine in a very strict, fixed ratio. And here's the absolutely crucial point. A compound develops entirely new properties. For example, hydrogen is a highly combustible gas, and oxygen heavily supports burning. But when they combine chemically to form the compound we know as water, H2O, they create a liquid that actually extinguishes fire. Isn't that just amazing?
Now, over on the other side of the matter family tree, we have mixtures. Mixtures simply combine things physically without any sort of chemical reaction taking place. And we divide these into two types. First up are homogeneous mixtures. These look completely uniform throughout. If you dissolve a spoonful of salt into a glass of water or look at a piece of brass, you cannot see the individual components. It just looks like one single phase. Then we have heterogeneous mixtures. And these are different. They have a non-uniform composition with clearly visible boundaries. If you try to mix oil and water, they clearly separate into distinct layers. You can easily see the different parts right there with your own eyes.
Please don't worry if this next part feels a little tricky at first. We are at Section 3, Solutions, Suspensions, and Colloids. I'd encourage you to take a moment and copy this table into your notebooks, as it so neatly contrasts our three main types of mixtures. Let's look at the size row first. Solutions, like sugar water, have tiny particles, less than 1 nanometer in size. They are completely invisible and very stable, meaning they never settle at the bottom. Now, let's contrast that with suspensions. Suspensions, like chalk mixed into water, are the exact opposite. Their particles are large, greater than 100 nanometers. You can actually see them, and if you leave the mixture undisturbed, they will eventually settle all the way to the bottom, which makes them unstable. Finally, we have colloids. Colloids, like the milk we talked about earlier, sit right there in the middle. Their particles are between 1 and 100 nanometers. So they are invisible to the naked eye and stable like a solution, but they have a very special property. Their particles are just large enough to scatter light, which true solutions simply cannot do. Let's move forward and see how this builds into measuring these mixtures. When analyzing a solution, scientists often need to know its concentration. Concentration simply tells us exactly how much solute, which is just the solid substance being dissolved like sugar, is hiding in the given amount of our liquid solvent, like water. Just think of it like making a cup of tea. If you put in 1 single teaspoon of sugar, it has a low concentration. But if you put in 5 teaspoons, you've created a highly concentrated solution. Let's carefully walk through how to calculate this, step by step, using the mass by mass percentage formula. It's actually very logical. Step 1. Identify the mass of your solute. Let's say we have 10 grams of salt. Step 2. Identify the mass of your solvent. We'll use 90 grams of water. Step 3. We just add them together to find the total mass of the solution. So 10 plus 90 gives us 100 grams total. And finally, step 4, we divide the mass of the solute by the total mass of the solution and multiply that by 100 to get a percentage. So 10 divided by 100 is 0.10, and times 100 gives us a neat, easy 10% concentration. Take your time with this formula. It is a wonderful tool to have in your scientific toolkit.
We've discussed particle sizes and concentration. So let's move forward to section 4, understanding the Tyndall effect. Imagine a magnificent beam of sunlight piercing through a dense forest mist. That brilliantly illustrates the Tyndall effect. Remember how we just said colloidal particles are just big enough to scatter light? Well, because mist acts as a colloid, it consists of tiny liquid water droplets suspended right there in the air. Those droplets are exactly the right size to scatter the sun's rays in all directions. This scattering makes the actual path of the light magically visible to our eyes. A true solution, like clear salt water, wouldn't do this at all, because its particles are just too small to catch the light.
To fully understand colloids, we really just need to learn 2 quick terms. Every colloid has 2 parts. The first is the dispersed phase. These are the solute-like particles that are distributed throughout the mixture, like those tiny water droplets in our forest mist. The second part is the dispersion medium. This is the substance holding those particles, like the air in the forest. And depending on what state of matter is mixing with what, you get some incredible everyday items. Fog is liquid dispersed in a gas. Shaving cream is a gas dispersed in a liquid. And our old friend milk? That is actually a liquid dispersed in a liquid.
You are doing wonderfully. For our final topic today, let's dive into section 5, physical versus chemical changes.
Matter is always changing, but it changes in 2 very distinct ways. A physical change alters the state, shape, or appearance of something, but its core chemical identity remains exactly the same. Melting ice into water, or maybe melting butter in a warm pan, are physical changes. They are usually quite reversible. You can just freeze that water right back into ice. A chemical change, however, is a chemical reaction. It creates entirely new substances with totally different properties. Burning wood or lighting a candle is a chemical change. The wood reacts with oxygen. It turns into ash and gases, and you cannot easily reverse that process to get your log back. These changes are, for all practical purposes, irreversible.
As we gently wrap up our journey today, I want to leave you with a thought. Look closely at the world around you. Is anything you see truly scientifically pure? The air you breathe, the soil beneath your feet, the beverages you drink, they are all magnificent, incredibly complex mixtures. Thank you so much for your patience, your wonderful focus, and for taking notes with me today. I really hope this explainer has inspired you to look at your everyday world through the fascinating analytical lens of a chemist. Until next time, keep exploring.